Hello class, this is CSE-5250, sections 2 and 60, also week 2, spring 2026. So, we're going to begin with chapter 4. Last video I talked about chapters 1 and 2. We are going to skip chapter 3. We're going to cycle back to that later in the term, because that chapter 3 is MPI. I feel like that's a bit trickier to work with, and even more so if you are working using a Windows machine. I'll talk about how you can work on the labs using a Windows machine when we get to OpenMP and MPI. But for pthreads, we must be working with a Unix machine because, well, it's just easier to compile the code that way. So as I said, this is chapter 4. And we begin with a review of what processes and threads are. So a process is an instance of a running program. It consists of the code that is loaded into memory, but also consists of memory allocated to the program itself. So if you recall from operating systems, when a process is loaded into memory, of course we have the code loaded into memory as well, but we also have code allocated for the stack and the heap. There's also other things loaded into memory, such as information regarding the state of the program, such as whether the program, or I should say process, is blocked or it's ready to run. There's also information about what files are allocated to the process. And not just files, just other resources in general. One thing about processes is they think they have the whole computer to themselves. For the most part, and with exceptions such as shared memory, processes don't know other processes exist. I guess yet another example to that would be something closer to MPI, where they send messages to one another. But for the most part, a process's memory is private, and processes think they have the whole computer to themselves. Turns out none of that is suitable for a shared memory program, because by default each process's memory is private and no other process can access it, unless there's a shared memory setup or a message passing interface. There's no way we can get stuff from one process to another. There is another way, but we have to give up on processes entirely. We have to use something called lightweight processes, or better known as threads. So when a process starts up, what begins as executable code in a program, though that might not always be the case for some instances, like Python is interpreted code, Java is code that is loaded into its own virtual machine. But generally speaking, a program starts out as code, then it's loaded into memory. It's loaded by the system as a process, and then this process can create multiple lightweight processes, or threads, each with access to the same memory as the original process. It's called a lightweight process because it has some of the same things as normal processes, but it has fewer things typically associated with processes. So processes can't share things with one another. Threads can. So when a process creates multiple threads, all those threads can share the same resources in memory as the original thread, as the parent thread. Think of a thread as a sequence of statements in a program. A shared memory program is one process, but there can be multiple threads. There are several examples that you may have read about. One example that was talked about in an operating systems textbook that I have is a word processor. Imagine a word processor that has 3 threads. One renders text on the screen, another listens to user input, and yet another does the autosave operations. So, if this were a single-threaded program, where one thread has to handle listening to user input, rendering stuff on the screen, and saving to a file, if that program is in the middle of saving, it cannot respond to anything from the user until it is finished. Also, if you try to press something and it's in the middle of rendering something else, it won't render the text right away. So by making a multi-threaded program is how we can make a program do multiple tasks. Though that is task parallelism. So that's a little bit different from what we want here. That is data parallelism, where multiple threads are executing the same code on different data. I guess yet another example would be a video game. Say you have one thread for the physics engine, another thread for user input. And if this is an online game, maybe you have yet another thread for communication over a network. Oh, and another thread for the sound engine, because sound effects in a video game. So we are going to get started with a simple Hello World program written in C using the pthreads library. Again, we have to program this on a Unix machine because it's just easier that way. So let me exit from the PowerPoint slides and let's get to work on coding this bad boy. So I need to create a new file. I'm just gonna do this. So vi hello.c, press enter. That's just going to open a code editor within the terminal. I already had the terminal open. If you want to open the terminal, just right click open terminal and it'll just open a terminal. What I'm going to do is press escape, press :WQ, press enter. That's going to create my code file here. Now you can just start writing code in that code editor, but I personally prefer a GUI-based interface for writing my code. That's just me. Code your programs however you're comfortable with. Use whatever tools you are most comfortable with. I'm just using the GUI-based text editor that Ubuntu has. Alright, let's begin. Let's zoom in. We're going to begin with some includes directives, so standard io.h, standard lib.h, and finally pthread.h. That last one is, of course, the pthreads library. I am also going to write a few comments just because it's a good idea to comment your own code. That's the wrong comment symbol. Okay. One thing we need is a global variable that denotes how many threads there are in the program. So that's a thread count. We need to write a function that our threads are going to run. So this is a function prototype though. So a function prototype is just the function signature. So this is a hello world function, but its data type is void star. Let's call it hello. And we're passing in a parameter of data type void star. When you see the word rank, word rank, that just means, say, thread 0 out of such and such, thread 1 out of such and such. It is a thread identifier. So that way we can number each thread with a unique rank. We can tell which thread is which. let's write that main function. If you're not familiar with what I'm going to type, that is int main, and then in parentheses, int argc, comma, character, star argv, square brackets. That's just a means of typing in command line arguments that can then be passed into the program. So when we run this program using /program name, we can type in after that the number of threads we wish the program to run with. Let's create a long variable, call it thread. That's just a 64-bit integer, though technically speaking, it might not always be 64 bits. Don't worry about that for now, but if you are worried about that, you can use the, there is a set of alternate data types that is meant to be the same size regardless of the computer system itself. You can use those if you want. I'm just going to use long because, well, it's just easier that way. And I actually forgot them. Sorry. Okay, so that's just a variable that we're going to be using in a for loop. So don't worry too much about that. You could just replace it with int if you wanted to. Next, we need to create a variable for our thread handle. So that is of data type pthread t star. So this is actually two things at once. One, we need our thread handles, which is of data type pthread t, but we don't know how many threads we're gonna have ahead of time, so we're just gonna dynamically allocate memory for our thread handles. So this is actually gonna be an array of thread handles. Before we get to that, let's get the number of threads to run for the command line. So that is thread count. So the variable thread count, we're going to assign it a value here. That is strtol, so string to long, argv1, comma, null, comma, 10. So when you run this program, you're going to be typing something like /hello 10. That 10 means run this with 10 threads. So argv0 that's just the program name. Argv1, that is the string that represents our number 10. We have to convert that from a string to an integer data type, so technically long. That way we know how. That way we effectively tell the program to run with this many threads. All right, let's keep going. Now we get to allocate memory for our thread handles. So thread handles equals malloc, and then we have to pass in how much memory to allocate. So that's going to be thread count denotes how many threads we have, so we can just say thread count and then multiply that by however big a pthread t is. So we can just say thread count times size of pthread t. There we go. Okay, so here's where we get the program to create new threads. The base function for that is pthread create. I'm going to say address thread handles 0, comma, null, comma, hello, 0. So, and I will explain this more in detail. the first thing you pass in is an address to your thread handle. I'm just saying thread handle 0. So it could just be, so this is just going to be an address to a thread handle. The second thing to pass in, just pass in null. The third thing to pass in is the name of the function you want your thread to run. And the fourth thing we're passing in is something that's being passed into the hello function. So I typed in 0 because this is going to be thread 0 of 0. So this thread handles, this is an array of thread handles. We're passing in the address of the 0th element of that array. So if you want to generalize this code, we actually need to stuff this into a for loop. So let me just add a comment. Create threads and then have each call the hello function. So for thread equals 0, thread is less than thread count, thread plus plus. So now instead of pthread ampersand thread handles 0, that's going to be thread handles thread. Pretend this thread is just an I, so it would be, so you might be more familiar with for int I equals 0. If I just did that instead and replaced I with that, and then the 0 with I, it's basically the same thing. The program just has the code in the slides has us doing this instead. But if you want it to make a little bit more sense, I guess you can just cut that from there and then just have the thread variable defined at this level, right before the for loop. That might make a little bit more sense because, at least for me, I like related variables to be close to one another. Variables and associated code in which that variable is used, I like them to be close together. If possible, at least. So now we have a for loop that's going to repeatedly call pthread create for however many threads we want the program to run with. Oh, one more thing. I actually forgot to cast this thread value from long to void star. So that is one thing we have to do, because this function, it takes in arguments of data type void star. So we have to cast this from long to void star. Yeah, don't forget that, or else the program might just break. Okay, at this point, the program has created threads. Let's now have the main thread do something else. We can just have it say hello. Main thread says hello. Printf. Hello world from the main thread. Alright, so now, at this point, these threads are now doing their own thing. The parent thread should simply just wait for all those threads to finish. We do that by, well, the primary function for that is pthread join. So pthread join, we pass in a thread handle, but without the ampersand this time. Thread handles 0, and then for the second thing to pass in, let's just pass in null. Again, we won't know ahead of time how many threads this program will run for. So once again, we are gonna have to stuff this code inside of a for loop, and we're gonna write code like that. Let's just replace that 0 with thread. So this is gonna call pthread join for however many thread handles we have. We're almost done. Because we have allocated memory for our thread handles, once we're done, we have to deallocate that memory. So that is a simple operation. Free thread handles. And now the program is done. Return 0. Okay, we're almost done with the program. The main function is done, but we still have to flesh out the hello function. So let me just copy that. So we're just going to implement that. We're going to create a long variable called myRank. And we passed in the rank as data type void star, but now we have to cast that back as a log. So long rank. And again, think of rank as thread 0 of however many threads we have. Thread 1, thread 2, thread 3. So think of the rank as a thread identifier. It's a different identifier in system memory, but we're just going to enumerate our threads from 0 to however many threads we have. And with that information, we can then write our next printf statement. Hello world from thread. I'm going to write in a placeholder %ld of, and then another placeholder %d. And those placeholders are going to represent my rank and thread count. So it's literally going to say hello world from thread 0 of 10, 1 of 10, 2 of 10, 3 of 10. And this function is returning nothing, but we have to have it return null. Alright, so now the program is done. I'm going to minimize that, and then the command to run the program is as follows. gcc-g -W wall -o, the name of the program without the file extension, or rather, the name of the executable we want to give this file. Let's just call it hello. The name of the source code file, that is hello.c, and then -lp thread. If this works, I should not get any issues. Okay, it worked. Now we have our executable right there. So for us to run it, all we have to do is do /hello. Not quite. Because this program is expecting a command line argument that denotes however the number of threads we want to run this program with, we can't just type /hello. It's going to set fault if we do. I have to type /hello and then some number of threads. And now we have hello world from thread 0, 1, 2, 3, 5, 4, 8, 9, and then hello world from the main thread, 6 and 7. It is not going to run sequentially. That is normal. Oh, a few things about the compile command. -wall, that is short for warn all. It enables warning messages that helps you write cleaner code. It's recommended that you type in -wall. Not strictly required, but good idea for writing better code. Also, the -lp thread might not be needed on some systems. Right. So let's take a rundown. Let's do a rundown of what that code is doing. Okay, so obviously we need. So the obvious thing in this code is pthread.h. That is just the library for pthreads. Right there. We have a global variable that every thread can access. We have the main function set up to accept command line arguments. We have this function strtol, strtol, that converts our command line arguments from string to long data type. This accepts 3 arguments. The first thing is the string to parse as a number. That's the first argument. The second argument, just pass in null for that. And the third argument is the base. We want it in base 10, therefore type in the number 10 as the third argument. pthread t star, as I said, that is the data type for our thread handle. For each thread, we need a thread handle, but because we don't know how many threads we are running this program with, we must dynamically allocate memory for an array of thread handles. So once again, there are 2 things going on here. One is we need a thread handle, but we need to dynamically allocate memory for our thread handles because we don't know how many threads we are working with ahead of time. pthread create is your function you use to create a new thread. Because we have multiple threads, we're just gonna use pthread create within a for loop to create our threads. This is a function that takes in 4 arguments. The first one is a pointer to your thread handle, which we have to allocate ahead of time because, again, we're allocating an entire dynamically allocated array worth of thread handles. The second argument, just pass in null for that. The third argument is the name of the function that the thread is going to execute. And the fourth thing to pass in is function arguments to be passed into the function specified for the third argument. The third and fourth arguments are of type void star. That type can be cast to any pointer in C. For the fourth argument, that allows for multiple values to be passed into the thread function as a list of values. Similarly, the return type of void star allows the function to return multiple values. So that's what's going on with the void star. That is the data type used for both the function to be called by the threads and anything being passed into that function. So once all that is done, the main thread says hello. Once a thread has finished, we call pthread join. That is a function that takes in 2 arguments. The first one is just the thread handle, and the second one is you pass in a variable so that it can receive any return values from the thread. We don't have anything being returned from our hello function, so that's why in this hello world program, we just passed in null. So the act of a main thread creating multiple threads and then waiting for them to finish, that is the fork and join model. So the main thread forks by calling pthread join. No, the main thread forks by calling not pthread join, but rather pthread create. The join part of the fork and join model is accomplished by calling pthread join. You call pthread join for every thread you have. If you don't do that, you might get zombie threads. They're just gonna suck. They are going to hold on to resources that you're going to need for other threads. So if you have these zombie threads, they're not gonna let go of the resources and they might prevent the creation of new threads. If the main thread does not need to wait for a thread to finish, instead of calling pthread join, call pthread detach. That way, a thread's resources is freed up upon termination, and the main thread does not have to wait. Oh yeah, another thing, every function associated with the pthreads library returns an error code. We're not going to be using the error codes here, but it's a good idea to use them because that way it's using the error codes, it's useful for debugging if you need to do any sort of debugging. So that Hello World program is actually going to be your first programming assignment. It's going to be rather short, so I'll have it tentatively due on the Wednesday of next week. So that's programming assignment 0, programming assignment 1, you're going to implement a parallel algorithm for estimating the value of pi. So, this is going to demonstrate an issue that is to be expected when you write multi-threaded anything. The textbook has an example of matrix vector multiplication. So, consider an array in which each element is being accessed by a separate thread. The textbook uses matrix vector multiplication, but an even simpler example would be vector addition. So, say you have a 1000 element vector and another 1000 element vector, and you're trying to add them and store them, the result, into, say, another 1000 element vector. So, for example, we would have the 357th element be calculated by a thread, and then the 358th element be calculated by another thread, and then the 359th element calculated by another thread. That's just one implementation we can do. And a different way would be to have, if you have 1000 elements and 4 threads, have the first thread do the first 250 elements, and the next thread does the next 250 elements after that. Either way, each element in the resulting vector is calculated by a separate thread. In other words, each element is accessed by one unique thread. No element is accessed by more than one thread. Here's a situation where that's not the case. What if there is some variable that more than one thread needs to access or modify? Such as this summation for the number pi. So, this is a formula that estimates the number of pi. We can express this as an infinite sum, by the way. Something like this requires calculating a lot of terms to get an accurate answer, which is perfect for us, because if we're going to calculate lots of terms, maybe we could speed that up by parallelizing it. Here is what the relevant snippet of code would look like as a single threaded operation. We have a single for loop that calculates one term at a time in this sum, and then it's going to add that to a running total, which you just call sum. Though it's a lot more complicated than that, because there is a -1. Each term is multiplied by -1 every other term. So we have to flip the sign from 1 to -1, alternating. So this is an alternating sum. We can just do that by, in addition to saying I++, we also say factor equals negative factor. So the factor is just 1. By saying factor equals negative factor, we alternate the sum, so every other term is negative. Of course, this isn't the full sum. We have to multiply it by 4 to get the number pi. So that is a single threaded implementation. If you want to achieve parallel operation given n terms and p threads, each thread should be given n over p terms to compute. For that to work, so if this is a single threaded operation, that single thread is going to calculate all the terms one after another. But because we need to divide the work between multiple threads, we have to rewrite our for loop in such a way that each thread has its own starting and stopping position. It would look something like this. Yeah, that's quite a lot. And this is what makes parallel programming a lot trickier than serial programming. So consider a simple example with, say, 100 terms. So p equals 1 and n equals 1. A single-threaded implementation simply adds all 100 terms sequentially. So it calculates term 0, and then calculates term 1, term 2, all the way to terms 97 98, and 99. If we have a 4-thread implementation, now we have something like this. So P equals 4. That means each thread must do 25 consecutive calculations. So thread 0 calculates and adds terms 0 to 24. Thread 1 does terms 25 to 49. Thread 2 does terms 50 to 74. Thread 3 does terms 75 to 99. Also notice that I have the code snippets hard-coded for 0 to 25, 25 to 50, 50 to 75, 75 to 100. I just did that to illustrate. I just did that for illustration purposes. But in the code, you would have this. You would have these values, my first I and my last I, calculated for each thread. So each thread calculates its own my first I and its own my last I. So thread 0 calculates terms 0 to 24. So technically it has to be term 25. So thread 0's my first I is 0, and then it's my last, and then that same thread's my last I is term 25. Similarly, the next thread after that is 25 to 50. The next thread after that is 50 to 75. The next thread after that is 75 to 100. Ultimately, we want our program to work regardless of how many threads it's running with. So this is why we have to go through all the effort of calculating a my first I and a my last I. This is in addition to having to add terms whose sign is alternating. So every other term is negative still. Put it all together. Given p threads and n terms, the ith thread is assigned to calculate the ith portion of n over p terms. That thread calculates its starting and stopping positions for its for loop. Then it calculates each term one by one, adding each term's value to the global variable of sum. Finally, the loop stops and the thread has finished its work. So this is what the code for that would look like. So this is just all the preliminary stuffs. All the include directives, global variables, and the necessary function prototype. Everything after that, that's just the main function. So a lot of it is modeled off of our hello world function, where we have to allocate memory for our thread handles. We have to then, so in our hello world function, we had to get the number of threads passed into the program, but here we also have to pass in the number of terms, because this program, we are going to code this program such that it's going to create an estimate for pi based on how many terms we want. And here's the thread function. So it's going to do a portion of the work in calculating the estimated value for pi. When you run this program, be sure to type in the number of threads to use, followed by the number of terms to add. If you forget any of that, you're gonna get a seg fault. When you do program this, keep in mind that there are no safeguards for when the number of threads does not perfectly divide the number of terms. That is a bug fix that we'll do in a later step. Right now, just make sure that the number of threads perfectly even divides the number of terms. Later on, I'll have you code this pi estimating program in its rough state, and then you're gonna try it out. This assignment is going to be tentatively due next Friday, so I may have to adjust it just to make sure you're all caught up. But this is a quirk of the program that we have to address as well. When you run this program with, say, 10 threads and 100,000 terms, you'll notice that the estimated value of pi is changing every time it runs. Now we want our estimate to be deterministic. That is, we don't want any randomness affecting the final estimate. But that's actually what we're getting here. We're getting some randomness here. What gives? It only gets worse if you add more threads. But it appears to be absent when we only have one thread. And that's because we have a critical section. We have a section of code that's being accessed by more than one thread. So here's a simple example of what we have. So a critical section is a region of code in which multiple threads, it's a section of code in which multiple threads is going to try to access something. So say we have two threads accessing a shared variable that has a value of 30 assigned to it. Thread 0 is going to try to add the number 3. Thread 1 is going to try to add the number 5. The expected answer is 3 plus 5 plus 8. No, 30 plus 3 plus 5, that is 38. That is our expected answer. But that is not what we're going to get. Neither thread knows that there's another thread trying to add something to that same shared variable. So what happens is this. Both threads access that shared variable at once. Reading is okay. Reading by multiple threads reading the same shared variable at a time is okay. We only have problems when we try to write to it. So now both threads have the number 30 copied to their own memory. They're now going to add their own respective values to that. Then we get the numbers 33 and 35. Our expected answer is 38, so that's not correct. And now, each thread is going to store its result back into that shared variable. So one thread stores the number 33, and another thread stores the number 35. However, it's also possible that it might be the other way around. So the 35 gets stored first, and then the 33. But the expected answer, it's supposed to be 38. Not only did we get 2 wrong answers, we lost one of them. This is a race condition. It's called that because these threads are trying to race to get their data written in some memory slot. But the thing about a race condition is last place wins. In a race condition, last place wins. If you're the first to get something written into a memory slot, you are the first to have your data overwritten. Last place wins. So I'll have you program I'm just going to tentatively assign to you programming assignment 1 alongside programming assignment 0. Next week I'll have a complimentary video that shows you how to write the pi estimating program. All the instructions as well. So you are currently assigned programming assignment 0. That is writing the hello world program and then trying it out. I'll also assign to you programming assignment 1. That is just getting started with the pi estimating program. Okay? Alright. So, to cap it all off, race conditions happen when threads are trying to access, though I guess I should say write to a shared variable. We need a means of keeping threads from reading the shared variable while another thread is updating it. That is called mutual exclusion, often abbreviated as mutex. In our pi estimating program, having a race condition means we are missing terms in our calculation of pi. Not a lot, but at the same time, this is bad because now we have a non-deterministic program. The result of our estimate is going to change every time we run the program, which is bad. Because we want it to produce the same result every single time. Alright, so that's going to be it for this video. I'll give you programming assignment 0 and 1. I'll have a follow-up video next week about how to code the pi estimating program. But for now, just focus on the Hello World program and see how far you can get. And then see how far you can get with the pi estimating program. Okay? Alright, that's gonna be it for week 2. Week 3, as I said, I'll continue our discussion on our pi estimating program by, well, showing you how you would code it, okay? And then we're gonna try to fix all those bugs, okay? Alright, see you next week.